In the preceding lecture and in this lecture, we have learned to interpret the meaning of the molar entropy for a pure substance at any temperature by focusing on the contribution from translational, vibrational, rotational motions, conformational characteristics, and residual entropy, evaluating the entropy changes associated with phase change. We will now make use of these molar entropies under standard conditions to shine some light on the spontaneity of chemical reactions. At this stage of the course, we have not learned about the effect of mixing on the properties of molecules. So we must restrict our discussion to the consideration of standard conditions. That is, the reaction conditions where reactants and products are assumed to be pure and at 1 bar. While such conditions may or may not be very realistic, we will show in Chapter 4 that the present calculations are nevertheless very useful. For a quantitative description of standard reaction entropies, delta RS standard, that is the change in entropy for the reactive system as a result of the reaction under standard condition, we use the standard molar entropies of reactants and products. We write delta RS standard equal to the sum of the molar entropies of the products times their associated stoichiometric coefficients minus the sum of the molar entropies of the reactants times their associated stoichiometric coefficients. Let us consider the combustion of glycine as an example to illustrate the calculation. First, we write the balanced chemical reaction equation, recalling that each hydrogen atom ends up oxidized in the form of water, each carbon atom oxidized in the form of gaseous carbon dioxide, and each nitrogen atom in the form of nitrogen gas. Once we balance the number of carbon, hydrogen, and nitrogen atoms on both sides of the equation, we make sure the number of oxygen atoms is also balanced. For glycine, this leads to the following reaction equation with the associated stoichiometric coefficients of 9/4 for oxygen, 2 for CO2, 5/2 for H2O, and 1/2 for nitrogen, assuming the reaction is written for 1 mole of glycine. With these stoichiometric coefficients, we obtain delta RS standard equal to 2 times the molar entropy of CO2 gas plus 5/2 times the molar entropy of water liquid plus 1/2 times the molar entropy of molecular nitrogen for the products minus the molar entropy of glycine and 9/4 times the molar entropy of molecular oxygen gas for the reactants. Using the molar entropy values listed in the appendix of your book, we get delta RS standard equals to 2 times 213.74 plus 5/2 times 69.91 plus 1/2 times 191.61 minus 1 times 103.5 minus 9/4 times 205.14 equal to 133.0 joules per mole per Kelvin. Note that as expected from the increase in the number of moles of gas molecules during this reaction, from 9/4 or 2.25 to 2.5, the standard reaction entropy change is positive. To examine the spontaneity of this chemical reaction under standard conditions, we need to find the sign of delta RS standard for the universe. So far, we've only calculated delta RS standard for the system. We now need to do the same calculation for the surroundings. Recall that delta RS for the surroundings is equal to the heat for the surroundings divided by the temperature of the surroundings. Q surroundings is equal to minus the heat for the system, or Q sub P, since chemical reactions occur generally at constant pressure. Chemical reactions also occur isothermally, so the reaction temperature is the same as the surroundings temperature. Finally, Q sub P is equal to the standard reaction enthalpy change, or delta RH standard. So, delta RS standard for the surroundings is equal to minus delta RH standard for the system divided by the temperature of the reaction, obviously in Kelvin. For this reaction, calculating the sum of the standard formation enthalpies of products minus these for the reactants, accounting obviously for the stoichiometric coefficients, leads to a value of delta RH standards of minus 973 kilojoules per mole of reaction equation. Hence, delta RH standard for the surroundings is equal to minus 973 kilojoules per mole of reaction equation divided by 298.15 Kelvin, assuming, of course, that the reaction is carried out at 25 degrees Celsius. And this is equal to 3,260 joules per mole per Kelvin. So, the change in the standard entropy of reaction for the universe as a result of this combustion reaction is equal to delta RS standard for the system plus delta RS standard for the surroundings, or 133 joules per Kelvin per mole plus 3,260 joules per Kelvin per mole, or 3,393 joules per Kelvin per mole, which is a very large number that is positive. Hence, we conclude that under standard conditions, the combustion reaction of glycine is spontaneous. Note that all combustion reactions are strongly exothermic, that is, all exhibit very large negative delta RH standard. Hence, their delta RS standard for the surroundings are very large and positive, typically much larger than delta RS standard for the system. So, regardless of whether more or less moles of gas are formed during a combustion reaction, the heat released in the surroundings is sufficiently large to drive these reactions to be spontaneous under standard conditions. We now follow the same approach to evaluate the spontaneity of the complexation reaction between nicotinamide adenine dinucleotide, in short NAD+, and lactate dehydrogenase. We write the reaction as NAD+ plus lactate dehydrogenase forms the NAD+ plus enzyme complex. At 25 degrees Celsius and under a pH of 7, the standard entropy change for this process is minus 16.8 joules per mole per Kelvin. The entropy change is negative, as should be, because these two chemical units form some kind of a bond that reduces their relative freedom of motion. For this process, the standard enthalpy change is equal to minus 24.2 kilojoules per mole. Also negative as expected because specific bonding between the enzyme and the NAD+ moiety is formed. From these values, we calculate delta RS standard for the surroundings equal to plus 24.2 kilojoules per mole divided by 298.15 Kelvin, equal to 81.17 joules per mole per Kelvin. So, delta RS standard for the universe is equal to minus 16.8 plus 81.17 joules per mole per Kelvin, equal to 64.4 joules per mole per Kelvin. Since delta RS standard for the universe is positive, we can say that under standard conditions, the complexation process between NAD+ and lactate dehydrogenase is spontaneous.